Alright, hi everyone. So today we're going to be introducing you to EECS3215, the Embedded Systems course at York University. Alright, so the very first thing we're going to do is do a little housekeeping. So we're going to go over the basic details about the course. So the very first thing is to go over the course description. So this is an introduction to the design of embedded systems using both hardware and software. The topics include microcontrollers, architecture, programming, design, and implementation of embedded systems using FPGAs, or field programmable gate arrays. There are 2 lectures every week. Each is about an hour and a half long. There's a lab every week as well, and the course is 4 credits. There's a number of prerequisites in order to get into this class, and those prerequisites are being enforced. All right. So the other thing to talk about are the course learning outcomes. So it's one thing to look at that course description from the York site, but the other thing we need to do is to go over these outcomes, because those are really important about what you're going to get out of the class. And we will be assessing those, and we'll be talking about those a lot during the class. They really are the really important thing, because it's about your learning. So the first course learning outcome is that students will be able to select and utilize appropriate parallel, serial, and analog interfaces. So this is an important part about embedded systems, and this ties into the CAB Graduate Attribute Indicator 1A, that is use specialized engineering knowledge of design-specific components, systems, or processes to solve engineering problems. So we're really going to be getting at the heart of this aspect of embedded systems in the class. The next one we're going to talk about is students will be able to understand embedded microcontroller architecture, development, debugging, and testing. Those are all really important skills right there. And this again ties to the Canadian Engineering Accreditation Board graduate attributes. In this particular case, the Graduate Attribute Indicator 1G that we use at York. And that's use specialized engineering knowledge of design-specific components, systems, or processes to solve engineering problems. Next up, the next course learning outcome is students will be able to prototype embedded systems using microcontrollers and field programmable gate arrays. And this ties to 2 design graduate attributes. The first one, or the graduate attribute indicator, is integrate design subsystems into complete systems and decompose complex systems into smaller, more manageable subsystems. So this is really important, again, for embedded systems and in engineering in general, from a design perspective. Next, students will be able to design embedded software and hardware systems to address problems in important application domains under tight constraints. So again, this is an important aspect of engineering as well as embedded systems, and this ties into the knowledge base graduate attribute. And in this case, the graduate attribute indicator demonstrates skills in computer programming, data analysis, and graphical visualization. The last course learning outcome that we are doing in this class is students will be able to design, implement, and interface with standard and custom peripherals. And again, we tie this into the CAB, and here we're looking at graduate attribute indicator 4B, design 1, conceive design solutions to solve the defined problem. So these are things that will be coming through in the course. These are really, really important, and we'll be paying specific attention to these CLOs, or course learning outcomes. All right. So the next thing to point out is that there is a required textbook for this class. It's called Microcontrollers and Microcomputers, Principles of Software and Hardware Engineering. So Principles of Software and Hardware Engineering. It's this book right here. It's a fabulous textbook. It's in its 2nd edition, and it's by Frederick Cady, professor at a university in the United States. The book itself is designed to be generic in terms of microcontrollers, so it's not specific to one particular type. So that's actually an advantage when we talk about different types of microprocessors or computing platforms. There's another reference textbook as well that we can access as an ebook through the library called Computers as Components, Principles of Embedded Computing System Design, 3rd edition by Marilyn Wolf. And the link to the library site is right there. All right, so there's going to be a number of assessments throughout the semester. There'll be 1 lab per week, worth a total of 25% of your grade. So basically divide up that 25% by the number of labs, and there will be team lab reports due the week after your lab on Moodle as a PDF. So everyone will submit one of those. The Monday night lab that starts at 7 p.m. might get shifted to Friday afternoon. That'll be a point of discussion down the road. And let's see what else. We have flipped classrooms. So these are basically in-class homework sessions that we do. There'll be at least 5 of them during the semester. I'll give you a video ahead of time. You watch it, you come to class, and we do some work in class. You can do it with your friends, your colleagues in class. And so it's a really social kind of homework activity. And we do it using iClickers or Scantrons, depending on how the setup is. After that, there's that midterm that we have to do. It's worth 15% of your grade, and it's tentatively set for the 13th of February. There is a project that's due in this class. It's broken up into 4 different aspects, and that starts sort of mid-semester and goes on until the end of the semester. And it builds up, sort of spirals up, one piece at a time throughout the semester. Finally, there's a final exam. It's worth 20%, and it'll be held sometime during the final exam period. All right, so that lab that we're talking about, it's divided up into 3 stages. And those 3 stages correspond to the 3 hardware platforms and software platforms that we'll be using. And the idea is that there'll be basically the same applications being done with all 3 hardware platforms, and you'll be getting some reinforcement about those applications throughout. There'll be some similarity. It's a really good thing pedagogically. And the reason we're using 3 different platforms is because diversity really is important in engineering from a technical perspective as well, and helps us maintain objectivity and flexibility. And we'll be using these 3 different platforms to basically point out extensions to engineering design and ways forward into your engineering capstone class next year. So we'll be spiraling up in terms of complexity throughout the semester. We'll start off with FPGAs, and we'll do basically an intro to different parts and behaviors of embedded systems using that FPGA platform, the Altera DE2 board. After that, we're going to switch over to using existing peripherals with sort of software programming using the 9S12 microcontroller. It's a really classic microcontroller that has a lineage that dates back to the HC11 that was used throughout the 1980s and 90s. So it's a really classic, well-studied microcontroller. The latest version of it's called the Magna V. It's used a lot in automotive applications, and so that'll be the second half, or the second part of the lab session. After that, we're going to move on to customization of hardware and software using the Kinetis platform. It's a 32-bit ARM Cortex M0 Plus system, relatively inexpensive and low-powered, and it's basically going to form the lab kit that you can take home with you. You'll purchase it, you'll be able to take it with you, you'll be able to use it for your projects as well, and maybe use it in future projects. All right, so the basic lab schedule is broken down like this. So we start off early on with the Altera boards, right there. Then we're going to move on to the 9S12s. After that, sort of late January into mid-February. After reading week, you will do some soldering. Actually, there's 2 soldering sessions right there. Okay, and you will be using the Kinetis system basically throughout the end of February up until the beginning of April. So that there'll be a whole lot of hardware and software work throughout the semester. So once again, to reinforce what we're dealing with, we've got the Altera board, which is this board right here. It's an FPGA, or Field Programmable Gate Array. As well, there is the Dragon board, this one right here in the back. That has the 9S12 in it. So it's a 16-bit microcontroller. It's this board right here. The microcontroller is actually hidden underneath that breadboard right there. It has a bunch of buttons and displays and whatnot on it. It's a fabulous little microcontroller, big in this particular case in terms of the board. And then we're going to use these little Freedom boards. You're going to purchase these little things. They're in an Arduino form factor. You can see, in this case, one of the boards right here. It has a built-in LCD right there, so we can actually get some display on it. It's got the chip right there, and then there's what's referred to as a debugger or a programmer on it right there. And that allows you to plug in your board via USB and actually program it. And then you're going to build it up. You're going to add another board on top, and you're going to build up the hardware for that. You're going to build it up on a breadboard first, and then we're going to solder it. So you're going to learn some prototyping skills using breadboards, then some soldering skills as well, and you're going to interface all of that to that microprocessor board on the bottom. So there's going to be a whole lot of stages for these labs, and it's going to build you up forward towards that project that we need to do. So the project itself is going to be really a big part of this course. And you're going to work on an example embedded system with a specific application in mind that you come up with. So you're going to use that FPGA board if you want, but most of you are going to end up using these Kinetis boards because they're really flexible and inexpensive and easy to use. And so you can use either one, either the KL43Z board that you'll purchase or an FPGA of your choice. And then you get to choose sensors or actuation motors, things like that, of your choice based on the particular type of embedded systems application that you want to do. And each of you is going to do one of these. So this isn't a group project, it is an individual project, and you get to do it and take that home with you at the very end. We're going to run these projects in a similar way to how the capstone projects are done as well. And we're going to have sort of different levels of expectations, basically broken up into 4 different levels of below, marginal, meeting, and above or exceeding expectations. And basically what we're going to be looking for with these projects is that if you are meeting your expectations, or my expectations, you'll have a working system that has some commercial off-the-shelf parts, but there's maybe a lot of customization going on. If you go beyond that and you do a whole lot of custom work and it's elegant and insightful and really interesting as a project, then that would be really above the typical expectations for a project like this. But if you aim for that and you get it, that's awesome. If you've got a mostly working system, but it's mostly commercial off-the-shelf parts, so you bought the board, you bought a module that plugs into it, and you demonstrate that it works, well, that's good, but it's not what we really want to see. Okay, so that's marginally meeting expectations. Finally, if you haven't done any work or your thing is barely working, then that's really below the expectations of what we expect to see in this course. Okay, so we'll be using this 4-scale system. It's the one that's used basically in the Engineering 4000 capstone class as well. So we're trying to give you some practice so you can see what to expect in next year's design class. All right, so the project itself is broken up into a number of stages. The very first one is going to be a 140-character write-up that you do with a little graphic that shows the layout of what connects to what. And that'll be worth the 4% of the 25% of your project grade. And that's going to be due mid-February as an assignment on Moodle. Basically, submit in a 140-character description of it and a pin layout or a connection layout for your project, and that's worth 4%. Next up, at the same time, but in parallel to that, is a 140-character justification for the application. So why is this particular application of the hardware that you're putting together, so putting the stuff together and making it work, what good is it? Why is it an important engineering project? And that'll be worth 1% of the 25% of your project grade. And it's due as well on the 15th of February. So both of them relatively straightforward. We want you to put some thought into it, but it's not overly onerous in terms of what you actually have to deliver. So we want you to put some creative thought into it. After that, due on the 25th of March, so basically a month and some after that, is a demonstration video. And here what we're looking for is a demonstration of some hardware that you've purchased and you put together, maybe done some customization, some breadboard work on there. We want you to include a little bit of description of what you've done in terms of hardware update, in terms of pin layouts and some graphics like that, and 140 character update of your plan and justification for your project. So again, the write-up's really, really short, but we want to see you actually showing something. And that's going to be worth 10% of that 25% of your project grade, due on the 25th of March. After that, you're going to work to the end of the semester putting together a final demonstration video and a final report. The demonstration video is supposed to show your put together project doing what it was intended to do. The project video should be 3 minutes long, and it's worth 5% of that 25%, due on the 5th of April, basically the last day of class. There's a 200-word report, so not very long either, that gives a little bit more description as to what's going on. You'll be given a template that is structured as to how to write that up, but 200 words, not very long, but we want to see some technical detail in there as well. That's going to be worth 5% of your 25% of your project grade. So as you can see, this is a multi-stage project with components that are assessed at different parts of the project development, each worth a significant component of the overall grade. So as you progress through, you'll get grades and feedback as to what's going on with your project. That project is based on this personal lab kit that you're going to have, okay? Unless you choose to use an FPGA, which would be a different project. And we can talk about that later when we're in class. But the personal lab kit is going to be used if you both in that project as well as in the lab. And you're going to use them in the labs sort of after reading week. So you have to make sure to purchase that stuff ahead of time. You're going to get most of your parts or all the parts from vendors online or in the GTA area. So there's a list of different vendors that you can buy from. And on Moodle, I've created a spreadsheet that links both the components that you're supposed to get as well as multiple vendors that you can get them from. So that parts list and the vendor options are available on Moodle. Basically, it'll center around this Freedom KL43Z board, which is about $20. It's not very expensive. A wire kit, a jumper kit, so basically wires that can be used to bridge things on your breadboard. And as well, some sort of board that mounts onto your CPU board called a proto board or a shield. And you're going to get one of these 7-segment, 4-digit LED displays that goes on there, and some resistors that connect it up. And you're going to put all that together. And that'll be part of your personal lab kit. Okay, where do you get these things from? Well, there's a lot of places that you can get parts for this course. You know, the textbook comes from the bookstore, the library has reference books, that's all good. This is where York is in sort of the GTA. If you get stuff off the internet, that's fabulous, but you can also go to places like Sayal, it has multiple locations. You can go to Creatron, and the Home Hardware and College in Spadina, downtown, and multiple other places as well. I've given you enough detail about the components that if you choose not to use the vendors that are listed, then that's totally okay. There's up to 5 different vendors that you can go to that are in the list on Moodle. All right, so for next week, what you're going to do is you're going to work on the FPGA board. So this board right here. And you're going to do Lab A, and that Lab A is based on John Loomis's excellent Digital Lab 1 write-up that's available online. And then there's a specific thing that I want you to do at the very end and hand that in. And you'll see that in the lab description on Moodle. But basically what we're doing here is we're doing a behavioral examination of FPGAs. We're not getting into the details of Verilog initially. There's no reason to. Initially, what we want you to do is to get some hands-on experience with the FPGA board and to see what happens when you put the program in, how do you program it in the first place, and then flipping switches, how that changes the behavior on the LED display that's right there.